Let us see another important problem on continuity equation. The gap between a moving circular plate and a stationary surface is being continuously reduced as the circular plate comes down at a uniform speed of v towards the stationary bottom surface, as shown in the figure. In the process, the fluid contained between the two plates flows out radially. The fluid is assumed to be incompressible and inviscid. So here there is a surface and there is a moving plate that is coming downwards. So this is the moving plate that is coming downwards with the velocity v, and the distance between these two plates is h, and it is continuously reduced due to coming down of this moving plate. And it is said that the flow is incompressible. Incompressible means density is equal to constant. Inviscid means viscosity free. So viscous free fluid, that means viscosity, the fluids which have zero viscosity are called as inviscid, or we will neglect viscosity if any present. So the first question asked from this data is the radial velocity Vr at any radius r when the gap width is h is. The options are given. So what is radial velocity? The circular plate is pushing down and the fluid goes out radially. If this is the free surface, the fluid is going out radially, the plate is coming out in this direction, and this fluid is going out radially. At any particular radius, smaller radius, at any particular radius, the flow rate is equal to discharge is equal to area into velocity. A1 V1 is equal to A2 V2. So this is what continuity equation is. Continuity equation for incompressible and no accumulation of mass. If there is no accumulation of mass, then this equation should be used as continuity equation. So what is A1? A1 is this area, pi into r square, and velocity with which it is coming down. So it is coming down with velocity v is equal to area outside. So outlet area is the fluid from which area it is going outside, from this surface, this curved surface, the fluid is going outside. So what is the area of that curved cylinder? 2 pi r is the perimeter into the height h will be, into height h gives us area of that cylindrical surface. With which velocity is going outside? It is said that take that radial velocity as Vr. So Vr is equal to pi r square into v divided by 2 pi r h. Pi gets cancelled, r and 1 r gets cancelled. So v into r divided by 2h is the velocity. So option Vr by 2h, option A is the correct answer. And the second question from this data is the radial component of fluid acceleration at r is equal to r, capital R is. So radial component, if this is capital R, at this position, what is the acceleration? That is asked here. So how to find acceleration? We know that. And also here radial component has been asked. So acceleration is equal to, we don't know about the velocity is changing with respect to time or not. So do not consider it. And so dou v by dou t plus v into dou v by dou r. In case of rectangular coordinates, we will be taking x, but in case of this, we will be taking r. This is the radial component of fluid acceleration. So we no need this. So that is equal to 0. Acceleration is equal to, so Vr, radial velocity into dou VR by dou R. So what is VR? Velocity, radial velocity that we have got here is VR by 2h. So V into R divided by 2h. And dou V by dou R. Sorry, dou VR by dou R. So dou by dou R of V into R by 2h. So V is constant, 2h is constant, dou by dou R of R, that is equal to 1. So V by 2h. So V square into R by 4h square. So V square into R divided by 4h square is the answer. Where at any particular radius R, it is asked at R is equal to R is equal to capital R, that will be V square into capital R divided by 4h square. This is the answer. And another question we will see. The volumetric flow rate per unit depth between two streamlines having stream function psi1 and psi2 is. So remember this as discharge is equal to psi1 minus psi2 into unit depth. So this is the discharge. Remember this directly, but I'll explain how it has been obtained. For example, there is a stream tube or a pipe, and in this streamlines are present. So suppose this is streamline 1, this is streamline 2, and these are represented with stream function psi1 and psi2. Suppose I need to find a discharge. So the volumetric flow rate or discharge is, I am considering this part, and let me say this is x1 comma y1, this is x2 comma y2, and flow rate discharge is equal to area into velocity. So I am considering the elementary part. and that area will be, I am considering this as dy. So dy into unit depth as b. I am considering this unit depth as b. That will be inside the screen you are watching. So unit depth is b. That is the area. And what is the velocity? I am considering this side as velocity. So u. This is dq. So that is a elementary discharge. So integral dq is equal to integral u dy. So b is constant, unit depth is constant. I am taking it outside. So total discharge is equal to b into, so from where to where, y exists from y1 to y2, y1 to y2. So b into integral y1 to y2. We know that stream function dou psi by dou y is equal to u, and dou psi by dou x is equal to minus v. So we know this. So u is equal to dou psi by dou y, dy. But also this is x-axis and this is y-axis. Here x1 is equal to x2. Since I have taken this as a vertical line, x1 is equal to x2, that means x is equal to constant. X is equal to constant here. So we can write d psi is equal to dou psi by dou x dx plus dou psi by dou y dy. So as x is equal to constant, this will be 0. The change with respect to x is 0, and d psi is equal to dou psi by dou y dy. So substituting this in this equation, we will be getting q is equal to b into integral of y1 to y2. So this will be d psi. So b into psi y1 to y2. So the function for this first streamline is psi1, or you can write psi2 minus psi1 taking modulus. So that will be discharge. So that's why the answer is this one. And here it is asked that per unit depth will be cancelled, and the remaining is psi1 minus psi2 modulus.